Hello, I'm David Bolton of Go Parallel, and today I'm going to talk about the dangers of explicit multithreading. What can go wrong when you write your own threading code? What is a thread? A computer program is made up of at least one process which contains code to execute. The process allocates memory to hold the code, data, stack and heap. Plus there are other resources the processor needs such as security information, system resources like file handles and processor state. When a process is loaded into memory, a processor call will start executing the code. This is a thread of execution. Processors might have code that runs at a certain time on or at a regular interval. That's another thread of execution. A background thread that moves data between main memory and disk over an I/O channel, that's another thread of execution. So these are what threads are. As can be seen in Task Manager, many applications employ lots of threads. If your Task Manager doesn't show a threads column, click View, then select columns, scroll down and then just tick the appropriate box. Each processor call can only execute one thread at a time, but the operating system scheduler can suspend a thread and switch to another at any time, even during an instruction. If there's a flaw in a program that occurs when the timing or the ordering of the events affects the program's correctness, then that's called a race condition. A data race happens when two threads write to the same location at the same time without any locking or synchronizing. For example, a write to a non-aligned 32-bit variable is performed as two 32-bit writes with a bit of finagling. Unless access to the misaligned 32 bits is locked, it's possible that a data race can occur. The diagram shows 8 successive bytes but split into two 32-bit blocks. The blue bar shows an aligned 32-bit location while the red one shows a misaligned one, i.e. the start address is not a multiple of 4 and it crosses over the two 32-bit values. If the first 32-bit half of the misaligned variable is written to by one thread and the second is written by another thread, then tearing occurs and we have a bug. This can also happen with non-atomic writing, i.e. writing to variables stored in successive bytes. When two threads using different objects that are close in memory such that both share the same cache line, then false sharing can occur. This happens when writes to the memory cause a cache line to be invalidated and it needs to be refilled, causing a performance hit. Even though one of the objects might be reading, it's slowed down by the cache refill. The trick to getting around this is to keep the objects apart enough. Processors can use many threads, and these fall into two main categories, computing and I/O. As each CPU processor can only run one thread at a time, it's possible that more threads are needed than there are available cores. While it may be tempting to write your own thread management software, it makes a lot more sense to use thread pooling. This avoids the need to create threads, you just borrow them from the pool as needed. One problem with threads, particularly I/O threads, is that some will spend a long time doing nothing. I/O speed can be the order of microseconds, or with really slow devices, milliseconds per byte read. To avoid a thread just kicking its heels, you just need some kind of scheduler to reuse these threads. As you'll see on this screen, the Wikipedia scheduling page has a good list of the various scheduling algorithms available. Access to data between threads is a big problem and usually requires some kind of locking mechanism. In the C++11 thread library, for example, you can use a standard mutex to limit access by locking. Better still though, are lock-free methods such as in standard atomic for handling changes to multi-byte numerics. Mutexes are relatively slow, lock-free is best if possible. This C++ example shows an atomic int initially set to 10 then incremented. The standard atomic that creates a variable does not initialize it, so you should. There are various other thread situations to deal with. Access to global data from a thread, access to thread local data where each thread has its own data, and so on. Some of these require threads to be synchronized. In the example showing, the function threadfunc is run under thread T. The t.join line running in the main thread blocks execution until threadfunc finishes. In conclusion, I strongly suggest you avoid reinventing thread code because the chance of getting it wrong, introducing bugs, is very high. But if you're going to go down that way and you're not going down the OpenMP or Intel TBB route, then if you can, I suggest you use the new standard thread for the library in C++11. If you've got an earlier compiler, then the Portable Boost thread class comes highly recommended. Thank you for watching this video. I'm David Bolton with Go Parallel.